Imagine for a moment a vast, empty canvas, stretching infinitely in every direction. Now, picture a tiny dot appearing on that canvas, and then slowly, steadily, that dot begins to grow, expanding outwards, pushing against the emptiness around it. This is often how we intuitively visualize the expansion of our universe. A cosmic balloon inflating into some pre-existing void. A grand cosmic bubble pushing against the nothingness beyond its edges. It's a compelling image, one that our minds naturally gravitate towards because it aligns with our everyday experience. When a balloon inflates, it expands into the air around it. When a city grows, it expands into the surrounding countryside. Expansion, in our common understanding, requires an introduction. But here's where the universe, in its infinite wisdom and mind-bending complexity, challenges our most fundamental intuitions. The question, if nothing exists outside the universe, what is it expanding into? Is not just difficult to answer. It is, in a profound cosmological sense, a fundamentally flawed question. It's akin to asking, what is north of the North Pole? The question itself contains a premise that doesn't apply to the reality it seeks to describe. The North Pole is the northernmost point. There is no north beyond it. Similarly, the universe, by definition, is everything. If the universe is everything, then there is no outside for it to expand into. There is no pre-existing void, no empty canvas waiting to be filled. This isn't just a semantic trick, it's a cornerstone of modern cosmology, a concept that, once grasped, reshapes our entire understanding of reality. For centuries, humanity has grappled with the concept of the cosmos. Ancient civilizations envisioned a finite world, often enclosed by a celestial sphere. With the advent of modern astronomy, our horizons expanded, revealing a universe of stars, galaxies, and unimaginable distances. Yet, even as our telescopes peered deeper into the abyss, the question of its ultimate boundary, its edge, persisted. The idea of an infinite universe, while intellectually appealing, still left us with the nagging feeling that if it's infinite, how can it change? And if it's finite, what lies beyond its edge? The answer, as revealed by the groundbreaking discoveries of the 20th century, is far more subtle and elegant than a simple expansion into a void. It's an answer that forces us to abandon our terrestrial analogies and embrace a more abstract, yet ultimately more accurate, understanding of space itself. The universe is not expanding into anything. Instead, space itself is expanding. The very fabric of space-time, the four-dimensional canvas upon which all of existence is painted, is stretching. It's not that galaxies are moving through space, propelled by some unseen force into an empty expanse. Rather, the space between the galaxies is growing, carrying them along for the ride, much like raisins embedded in a rising loaf of bread. The raisins themselves don't move through the dough. The dough expands, increasing the distance between them. This distinction is crucial. It means that every point in the universe is, in a sense, the center of the expansion. From the perspective of any galaxy, all other galaxies appear to be receding, and the farther away they are, the faster they appear to recede. This isn't because they are all rushing away from a central explosion, but because the space between them is uniformly stretching. This stretching of space is not a movement within a pre-existing container. It is the creation of more space. The universe is, in essence, becoming more of itself. It is generating new space, new volume, from within its own structure. This concept is challenging because our brains are hardwired to think in 3 spatial dimensions, where expansion always implies a larger container. But the universe operates on a different set of rules governed by the intricate dance of gravity and the very geometry of space-time. To truly grasp this, we must shed the intuitive baggage of our everyday experience. The universe is not a balloon, inflating in your living room. It is the living room itself, expanding, with every point within it moving away from every other point. There is no outside of the living room for it to expand into, because the living room is everything. This fundamental shift in perspective is the first step towards understanding one of the most profound and counterintuitive truths about our cosmos. The universe expands by becoming more of itself, not by occupying more of something else. To delve deeper into this concept, we must first understand what we mean by space in the cosmological sense. It's not merely the empty void between objects, but an active, dynamic entity intrinsically linked with time to form space-time. Albert Einstein's theory of general relativity revolutionized our understanding of gravity, showing that it's not a force pulling objects together, but a curvature in the fabric of space-time caused by mass and energy. This fabric, far from being a static backdrop, is capable of stretching, bending, and even rippling. When we say the universe is expanding, we mean that this very fabric of space-time is stretching. Imagine a rubber sheet with dots drawn on it. If you stretch the sheet, the dots themselves don't move across the sheet. Rather, the sheet itself expands, increasing the distance between the dots. This is a 2-dimensional analogy for a 3-dimensional, or 4-dimensional, including time, phenomenon. The galaxies are like the dots, and the space between them is like the rubber sheet. They are not flying apart through pre-existing space. The space between them is growing, carrying them along. This stretching of space is uniform on large scales. Every observer, no matter where they are in the universe, would see galaxies receding from them in the same way. This is a crucial point that distinguishes cosmological expansion from an explosion. In an explosion, there's a clear center from which everything is moving outwards. But in the expanding universe, there is no single center. Every point can be considered the center, because the expansion is happening everywhere simultaneously. It's a bit like the surface of a balloon being inflated. If you draw dots on the surface of a deflated balloon and then inflate it, every dot moves away from every other dot, and no single dot is the center of the expansion on the surface. This concept of space itself expanding is fundamental to modern cosmology. It means that the universe isn't just getting bigger by filling up more empty room. It's creating that room as it goes. The volume of the universe is increasing because the metric of space, the very ruler by which we measure distances, is stretching. This stretching affects everything within the universe, but not in the way we might intuitively expect. For instance, galaxies themselves are not expanding, nor are stars, planets, or even atoms. These objects are held together by stronger local forces, gravity, electromagnetism, and the strong and weak nuclear forces that overcome the expansion of space on their scales. It's only on the largest scales, between gravitationally unbound structures like galaxy clusters, that the expansion of space becomes noticeable and dominant. Consider the light traveling from a distant galaxy to our telescopes. As this light journeys across billions of light years, the space it traverses is continuously expanding. This expansion stretches the wavelength of the light, shifting it towards the red end of the spectrum, a phenomenon known as cosmological redshift. This isn't a Doppler effect, like the change in pitch of a siren as it moves away from you, though it appears similar. Instead, it's the light wave itself being stretched by the expansion of space, providing direct observational evidence for the stretching fabric of the cosmos. This stretching is not a movement through space, but change in space itself. This dynamic nature of space-time, where space is not merely a passive container, but an active participant in the universe's evolution, is one of the most profound insights of the 20th century physics. It's a concept that challenges our everyday perceptions, but is essential for understanding the true nature of cosmic expansion. The universe is not expanding into anything. It is simply becoming larger, more voluminous, as the very fabric of its existence stretches and grows. How do we know all of this? How do we move beyond intuition and analogy to concrete scientific evidence? The story of cosmic expansion is one of meticulous observation and brilliant theoretical insight, beginning with the groundbreaking work of astronomers in the early 20th century. One of the most compelling pieces of evidence for an expanding universe comes from the phenomenon of cosmological redshift. You might be familiar with the Doppler effect, where the pitch of a siren changes as an ambulance moves towards or away from you. Similarly, the color of light from a moving object can shift. If an object is moving towards us, its light waves are compressed, shifting towards the blue end of the spectrum, a blue shift. If it's moving away, its light waves are stretched, shifting towards the red end, a red shift. For decades, astronomers observed that light from nearly all distant galaxies was redshifted, indicating they were moving away from us. The farther away a galaxy was, the greater its redshift, and thus the faster it appeared to be receding. This observation led Edwin Hubble, in 1929, to formulate what is now known as Hubble's law, which states that the velocity at which a galaxy is receding from us is directly proportional to its distance. This was a monumental discovery, providing the first strong observational evidence that the universe was not static, but dynamic and expanding. However, the cosmological redshift is not simply a Doppler effect. While galaxies are indeed moving through space, the dominant cause of the redshift for distant galaxies is the stretching of the light waves themselves as the space they travel through expands. Imagine a wave drawn on a rubber band. As you stretch the rubber band, the wave also stretches, increasing its wavelength. This is precisely what happens to light as it journeys across the expanding cosmos. The photons of light are literally stretched by the expansion of space, causing their wavelength to increase and shift towards the red end of the spectrum. This subtle but crucial distinction means that the galaxies aren't just flying away from us through space. The space between us and them is growing, carrying them apart. This cosmological redshift is observed uniformly in all directions, reinforcing the idea that there is no special center to the expansion. Every galaxy sees every other galaxy receding from it, just as every raisin in a rising loaf of bread sees every other raisin moving away. The universe is expanding everywhere, all at once. Another pillar of evidence for the expanding universe, and indeed for the Big Bang Theory itself, is the existence of the cosmic microwave background, or CMB. This faint, uniform glow of microwave radiation permeates the entire universe, a relic from a time when the universe was incredibly hot, dense, and opaque. For the first 380,000 years after the Big Bang, the universe was a superheated plasma, a soup of charged particles and photons. Light particles, or photons, were constantly scattering off these charged particles, unable to travel freely. The universe was effectively opaque, like being inside a star. As the universe expanded, it cooled. Eventually, the temperature dropped to a point where electrons could combine with protons to form neutral hydrogen atoms. This event, known as recombination, made the universe transparent to light. The photons that were once trapped were suddenly free to stream across the cosmos. These photons, released from the primordial plasma, have been traveling ever since, and as the universe continued to expand, their wavelengths have been stretched into the microwave portion of the electromagnetic spectrum. This is the CMB we observe today, the afterglow of the Big Bang, a snapshot of the universe when it was just a baby. The CMB is remarkably uniform across the sky, with tiny temperature fluctuations of only a few parts in 100,000. These minuscule variations are incredibly important, as they represent the seeds from which all the large-scale structures in the universe, galaxies, galaxy clusters, and superclusters, eventually grew. The existence, uniformity, and precise temperature fluctuations of the CMB are powerful confirmations of the Big Bang model and the ongoing expansion of the universe. It's a direct echo of the universe's fiery birth, a cosmic hum that tells us a story of expansion, cooling, and the formation of everything we see around us. Together, cosmological redshift and the cosmic microwave background provide overwhelming observational evidence for a universe that is not static, but dynamically expanding. They paint a consistent picture of a cosmos that began from an incredibly hot, dense state and has been growing ever since, with space itself stretching and carrying galaxies apart. But this expansion, as we've learned, is not just happening, it's accelerating. And that acceleration points to one of the most profound and mysterious components of our universe, dark energy. For decades after Hubble's discovery, astronomers assumed that the expansion of the universe, while ongoing, must be slowing down. Gravity, the dominant force on cosmic scales, pulls everything together. It was a logical assumption that the mutual gravitational attraction of all the matter in the universe would act as a brake on the expansion, causing it to decelerate over time. The big question was not if it was slowing down, but how much it was slowing down. This would determine the ultimate fate of the universe. Would it eventually stop expanding and collapse back in on itself in a big crunch? Or would it expand forever, but at an ever-decreasing rate? Then, in the late 1990s, two independent teams of astronomers studying distant supernovae made a truly astonishing discovery that completely upended this long-held assumption. Supernovae, particularly type Ia supernovae, are incredibly bright stellar explosions that serve as standard candles. Their intrinsic brightness is known, allowing astronomers to calculate their distance from Earth. By measuring the redshift of these distant supernovae and comparing it to their calculated distances, the teams expected to see evidence of a decelerating universe. Instead, To their utter shock, they found the opposite. The universe's expansion was not slowing down. It was accelerating. This was a monumental discovery, so unexpected that it initially met with skepticism. It was as if you threw an apple into the air, and instead of slowing down and falling back to Earth, it suddenly started speeding up and flying away faster and faster. This accelerating expansion implied the existence of a mysterious, unknown force, counteracting gravity on cosmic scales, pushing the universe apart. Scientists dubbed this enigmatic force dark energy. Dark energy is perhaps the greatest mystery in modern cosmology. We don't know what it is, but we know it's there because of its effects. It's estimated to make up about 68% of the total energy density of the universe, dwarfing both ordinary matter, the stuff we can see and interact with, and even dark matter, another mysterious component that interacts gravitationally but doesn't emit or absorb light. Unlike matter, which becomes diluted as the universe expands, dark energy appears to be a property of space itself. As space expands, more space is created, and with it, more dark energy. This means that, as the universe gets bigger, the influence of dark energy actually increases relative to matter, leading to an ever faster expansion. The leading candidate for dark energy is the cosmological constant, a concept first introduced by Albert Einstein in his equations of general relativity. Einstein initially introduced it to allow for a static universe, which was the prevailing view at the time. When Hubble discovered the expanding universe, Einstein famously called the cosmological constant his biggest blunder. However, the discovery of accelerating expansion has resurrected the cosmological constant, suggesting it might represent the energy of empty space itself, a vacuum energy that exerts a repulsive gravitational force. If this is true, then as space expands, the amount of this vacuum energy increases, driving the acceleration. Other theories for dark energy include new fields or modifications to gravity on cosmic scales, but the cosmological constant remains the simplest and most widely accepted explanation, even if its fundamental nature is still unknown. The accelerating expansion driven by dark energy has profound implications for the ultimate fate of the universe. If dark energy continues to dominate, the universe will expand forever, and at an ever-increasing rate. Galaxies will recede from each other so rapidly that eventually, even light from distant galaxies will be stretched beyond detection, leaving each galaxy isolated in a vast, empty, and cold cosmos, a scenario sometimes referred to as the Big Freeze or heat death. So, the universe is not just expanding, it's accelerating its expansion, driven by a force that makes up the vast majority of its energy content, yet remains almost entirely unknown. This adds another layer of complexity and wonder to the question of what the universe is expanding into, reinforcing the idea that it's not expanding into anything external, but rather that its internal dynamics are causing space itself to stretch at an ever-increasing pace. This brings us back to the fundamental question of the universe's boundaries and its overall geometry. If the universe is everything, and it's expanding, does it have an edge? Is it finite or infinite? And how does its shape influence this expansion? Cosmologists consider three main possibilities for the overall geometry or shape of the universe: flat, open, or closed. These geometries are determined by the universe's total density of matter and energy. If the density is exactly equal to a critical value, the universe is flat, like a sheet of paper extending infinitely. If the density is less than the critical value, it's open, like the surface of a saddle, also extending infinitely. If the density is greater than the critical value, it's closed, like the surface of a sphere, which is finite but has no edge. Current observations, particularly from the cosmic microwave background, strongly suggest that our universe is remarkably flat. This doesn't mean it's a two-dimensional plane. It means that, on large scales, the geometry of space is Euclidean, where parallel lines remain parallel, and the angles of a triangle add up to 180 degrees. A flat universe, if it extends infinitely, would have no boundaries or edges. It would simply go on forever. However, even if the universe is finite, it still wouldn't have an edge in the traditional sense. Imagine the surface of a sphere. It's a two-dimensional surface that is finite in area, but you can travel on it forever without ever encountering an edge or a boundary. Similarly, a finite, closed universe would be a three-dimensional analog of a sphere's surface. You could travel in any direction, and eventually, if you traveled far enough, you would return to your starting point without ever hitting a wall or an edge. This concept is incredibly difficult to visualize in our three-dimensional minds, but mathematically, it's perfectly consistent. So, whether the universe is infinite and flat or finite and closed, the answer to what is it expanding into remains the same. Nothing external. If it's infinite, it's simply becoming more infinite, with the distances between its constituent parts growing. If it's finite but closed, its volume is increasing, but it's still self-contained, expanding within its own structure without needing an external void. The expansion is an intrinsic property of space-time itself, not a movement into a larger container. The universe, therefore, expands by becoming more of itself. It's not filling a pre-existing emptiness, it's creating the space as it goes. This profound understanding, built upon decades of observation and theoretical breakthroughs, challenges our everyday intuition but offers a far more accurate and awe-inspiring picture of our cosmos. It tells us that the universe is a self-contained, dynamic entity, constantly evolving and forever expanding its own fabric, without needing an outside to grow into. The question itself, while natural for our limited human perspective, dissolves when confronted with the true nature of space-time and cosmic expansion. The universe is not expanding into anything, it is simply expanding. Let's delve deeper into the historical journey that led us to this profound understanding. For much of human history, our view of the cosmos was static and unchanging. From the geocentric models of Ptolemy to Newton's absolute space and time, the universe was largely conceived as a fixed stage upon which celestial bodies played out their eternal dance. Even Einstein, in his initial formulation of general relativity, introduced a cosmological constant to force a static universe, as the idea of a dynamic, expanding cosmos was simply too radical for the scientific consensus of his time. However, the seeds of change were already being sown. In the early 20th century, a series of groundbreaking observations and theoretical developments began to chip away at the static universe model. One of the pivotal figures in this revolution was Vesto Slipher, an American astronomer who, starting in 1912, meticulously measured the velocities of spiral nebulae, what we now know to be galaxies, using spectroscopy. To his surprise, he found that most of these nebulae were moving away from Earth at incredibly high speeds, indicated by the redshift of their light. Slipper's work provided the first empirical hint of a universe in motion, though he didn't fully grasp its cosmological implications. The theoretical framework for an expanding universe emerged from the equations of general relativity itself. In 1922, Russian physicist Alexander Friedmann derived a set of solutions to Einstein's field equations that described a dynamic universe, one that could either expand or contract. Independently, in 1927, Belgian priest and physicist Georges Lemaitre also found similar solutions and, crucially, proposed that the observed recession of spiral nebulae could be interpreted as evidence for an expanding universe. Lemaitre even went a step further, suggesting that if the universe was expanding, it must have been smaller and denser in the past, leading to the concept of a primeval atom, a concept that would later evolve into the Big Bang theory. However, it was Edwin Hubble who provided the definitive observational proof. Working at the Mount Wilson Observatory, Hubble, with the assistance of Henrietta Leavitt's work on Cepheid variable stars, was able to accurately measure the distances to these distant spiral nebulae. By combining his distance measurements with Slipher's velocity measurements, Hubble made the groundbreaking discovery in 1929. The farther away a galaxy is, the faster it is receding from us. This linear relationship, now known as Hubble's law, was the empirical cornerstone that firmly established the expansion of the universe. It was a paradigm shift, transforming our understanding of the cosmos from a static, unchanging entity to a dynamic, evolving one. This discovery wasn't just about galaxies moving apart. It was about the very fabric of space stretching. Imagine again our loaf of raisin bread. As the dough rises, the distance between any two raisins increases. The raisins themselves aren't moving through the dough. The dough itself is expanding, carrying the raisins along. Similarly, galaxies are not hurtling through a pre-existing static space. Instead, the space between them is expanding, causing them to drift apart. This is why we say the universe is expanding, not that galaxies are simply flying away from a central point. There is no central point to the expansion. Every point in the universe can be considered the center of the expansion, as all other points are receding from it. The concept of an expanding universe naturally led to the idea of a beginning. If the universe is expanding now, then in the past, it must have been smaller, denser, and hotter. Extrapolating backward in time, this leads to a point of infinite density and temperature, the singularity from which the universe emerged. This is the essence of the Big Bang theory, the prevailing cosmological model for the universe's earliest moments and subsequent evolution. The Big Bang was not an explosion in space, but an expansion of space itself. It was the genesis of space, time, matter, and energy, all originating from an incredibly hot, dense state. The Big Bang theory is supported by a wealth of observational evidence beyond just the expansion of the universe. One of the most compelling pieces, as we discussed, is the cosmic microwave background, CMB. This faint uniform glow of microwave radiation, detected coming from all directions in space, is the afterglow of the Big Bang. It's the residual heat from a time when the universe was so hot and dense that it was opaque to light. As the universe expanded and cooled, it eventually became transparent, allowing these photons to stream freely. Over billions of years, the continued expansion of space has stretched the wavelengths of these photons into the microwave part of the spectrum, making them detectable today. The CMB is a direct snapshot of the universe when it was only about 380,000 years old, providing powerful confirmation of the Big Bang model. Another crucial piece of evidence is the abundance of light elements. The Big Bang theory accurately predicts the observed cosmic abundances of hydrogen, helium, and lithium. In the first few minutes after the Big Bang, the universe was hot enough for nuclear fusion to occur, forming these light elements. The precise ratios of these elements observed in the oldest stars and gas clouds in the universe perfectly match the predictions of Big Bang nucleosynthesis, further solidifying the model. Furthermore, the large-scale structure of the universe, the distribution of galaxies, galaxy clusters, and vast cosmic voids also aligns with the Big Bang model. The tiny temperature fluctuations in the CMB, representing slight density variations in the early universe, served as the gravitational seeds for these structures to form over billions of years. Computer simulations based on the Big Bang model, incorporating these initial conditions, accurately reproduce the cosmic web of galaxies we observe today. So, the expansion of the universe is not just an isolated phenomenon, it is an integral part of the Big Bang narrative. It tells us that our universe has a history, a beginning, and an ongoing evolution. And this evolution is driven by the stretching of space itself, not by an outward movement into some external void. This understanding is crucial when we consider the next layer of complexity, the distinction between what we can observe and the universe as a whole. When we talk about the universe, it's important to distinguish between the observable universe and the universe as a whole. The observable universe is the portion of the cosmos that we can, in principle, see from Earth. It's a sphere centered on us, with a radius determined by how far light has had time to travel since the Big Bang. Because the universe has a finite age, approximately 13.8 billion years, and light travels at a finite speed, there's a cosmic horizon beyond which light has not yet had time to reach us. This means that the observable universe is constantly growing as light from more distant regions finally reaches us. However, the observable universe is not the entire universe. It's just our cosmic horizon, our personal sphere of visibility. We have no way of knowing what lies beyond this horizon, or even if the entire universe is finite or infinite. The expansion of the universe means that even if the universe is infinite, the observable portion of it is finite and growing. If the universe is finite, it could be much, much larger than our observable portion, or it could be just slightly larger. We simply don't know. This distinction is crucial when considering the question of what the universe is expanding into. Even if the entire universe is infinite, it can still expand. An infinite universe doesn't mean it's static. Imagine an infinite grid of points. If you double the distance between every single point on that grid, the grid remains infinite, but the distances between the points have increased. The infinite grid has expanded, but it hasn't expanded into anything because there was no outside for it to expand into in the first place. It simply became more infinite in terms of the spacing between its components. If the universe is finite, then it's often compared to the surface of a balloon. The surface of a balloon is a finite two-dimensional space but it has no edge or boundary. If you were an ant living on the surface of that balloon, you could walk in any direction forever and never fall off an edge. As the balloon inflates, the surface expands, and the distance between any 2 points on the surface increases. The surface itself is expanding, but it's not expanding into anything on the surface. It's expanding into the third dimension, but that third dimension is not part of the ant's two-dimensional universe. Similarly, if our three-dimensional universe is finite and curved, it could be expanding into a higher dimension that is inaccessible and irrelevant to our existence within it. The expansion is an intrinsic property of the universe itself, not a movement into an external container. The current cosmological data, particularly from the cosmic microwave background, suggests that the universe is remarkably flat. This means that on the largest scales, the geometry of space is Euclidean, where parallel lines remain parallel and the angles of a triangle sum to 180 degrees. A flat universe, if it is truly infinite, would have no boundaries and would simply continue to expand, with the distances between its constituent parts growing larger and larger. If it is flat but finite, it would be like a torus, a donut shape, or some other complex topology that is finite but unbounded. In either case, the expansion is an intrinsic stretching of space, not a movement into an external void. The concept of a universe without an edge, whether infinite or finite, but unbounded, is one of the most challenging for our human minds to grasp. Our everyday experience is confined to a finite, bounded world. But the universe operates on principles that transcend our immediate perceptions. The expansion is not about galaxies rushing into empty space. It's about the very fabric of space being created and stretched, increasing the distances between everything within it. This fundamental understanding is key to resolving the intuitive paradox of the universe, expanding into nothing. The accelerating expansion driven by dark energy has profound implications for the ultimate fate of the universe. For a long time, cosmologists debated two primary scenarios for the universe's end: the Big Crunch or the Big Freeze. The Big Crunch envisioned a universe where gravity would eventually overcome the expansion, causing everything to contract back into a hot, dense singularity, essentially reversing the Big Bang. The Big Freeze, or heat death, predicted a universe that would expand forever, but at an ever-decreasing rate, eventually becoming cold, dark, and empty as all stars died out and matter dispersed. However, the discovery of dark energy introduced a third, more chilling possibility, and indeed, the most likely scenario given current observations: the Big Rip or an accelerated Big Freeze. If dark energy is indeed a cosmological constant, an intrinsic property of space, then as space expands, more dark energy is created, leading to an ever-increasing repulsive force. This means the expansion will not only continue indefinitely, but will accelerate at an ever faster rate. In this scenario, the universe will become increasingly dilute. Galaxies will recede from each other so rapidly that eventually, even light from distant galaxies will be stretched beyond detection, leaving each galaxy isolated in a vast, empty, and cold cosmos. The night sky, billions of years from now, would be a desolate expanse, devoid of the familiar glow of other galaxies. But the implications of an accelerating expansion go even further. If the acceleration continues to increase, dark energy could eventually become so powerful that it overcomes even the local forces holding structures together. First, galaxy clusters would be torn apart. Then, individual galaxies would disintegrate, their stars flung into the void. Eventually, even stars and planets would be ripped apart, followed by atoms themselves, and finally, the very fabric of space-time would be shredded. This extreme scenario, known as the Big Rip, is a theoretical possibility if dark energy's density were to increase over time, rather than remaining constant. While current data favors a constant dark energy, the very existence of this mysterious force forces us to confront the most extreme possibilities for our cosmic future. Regardless of whether it's a big freeze or a big rip, the accelerating expansion means that the universe will continue to expand, becoming colder, emptier, and more isolated. This future is not one of collapse, but of increasing dispersion. It's a future where the question of what the universe is expanding into becomes even more poignant, as the distances between everything become truly astronomical, pushing the boundaries of our comprehension. This accelerating expansion also reinforces the idea that the universe is not expanding into anything external. If it were expanding into a pre-existing void, one might imagine it eventually filling that void or encountering its boundaries. But with dark energy driving an intrinsic expansion of space itself, the universe is simply creating more space, continuously, from within its own structure. It's a self-generating expansion, where the very act of expanding creates the room for further expansion. This is a concept that truly challenges our everyday experience, where growth always implies a larger container. But in the cosmos, the container itself is growing, and it is the growth of the container that defines the expansion. The nature of dark energy and its role in the universe's accelerating expansion remains one of the most active and exciting areas of research in cosmology. Scientists are employing a variety of observational techniques to better understand it, including studying distant supernovae, mapping the large-scale distribution of galaxies, and analyzing the subtle anisotropies in the cosmic microwave background. Each new piece of data helps to refine our models and narrow down the possibilities for this enigmatic force. The answers we find will not only tell us about the future of our universe, but also deepen our understanding of the fundamental laws of physics that govern its existence. It's a quest to understand the very essence of reality, driven by the perplexing observation that the universe is not just expanding, but speeding up as it does so. The human mind, shaped by millennia of experience in a three-dimensional, gravitationally bound world, struggles to conceptualize the universe on its grandest scales. Our intuition, honed by observing objects move through space, often fails us when confronted with the idea of space itself being dynamic. This is why the question, "What is the universe expanding into?" is so persistent, and why analogies, while helpful, can also be misleading if not carefully understood. Let's revisit the balloon analogy. While excellent for illustrating that there's no center to the expansion on the surface, and that distances between points increase as the surface expands, it often leads to the misconception that our three-dimensional universe is merely the surface of a four-dimensional sphere, expanding into a higher, unseen dimension. While mathematically possible and a useful conceptual tool, it's not necessarily a literal physical reality. The key takeaway from the balloon analogy is the intrinsic expansion of the surface, not the existence of an external dimension it's expanding into. For us, living within the three spatial dimensions of our universe, there is no outside to step into, no higher dimension to observe the expansion from. We are, in a sense, embedded within the expanding fabric itself. Another common misconception arises from thinking of the Big Bang as an explosion that happened at a specific point in space, with matter flying outwards into an empty void. This leads to the idea of a center of the universe, and an edge where the expansion is pushing against something. But as we've discussed, the Big Bang was an expansion of space, not in space. Every point in the universe was, in a sense, the location of the Big Bang. The expansion is happening everywhere, uniformly, on large scales. There is no central point from which everything is flying away, and therefore no outer edge to the expansion. The universe is unbounded, meaning it has no edges or boundaries, even if it might be finite in volume. Consider the concept of infinity. If the universe is truly infinite, then it has no boundaries. It stretches on forever in every direction. When an infinite universe expands, it doesn't become more infinite in the sense of gaining new territory. Rather, the distances between all its constituent parts increase. Imagine an infinite grid of numbers. If you stretch the grid so that the distance between 1 and 2 becomes twice as large, and the distance between 2 and 3 also doubles, and so on, the grid remains infinite, but the scale has changed. The universe, if infinite, is doing something similar. It's not expanding into a larger container, it's simply scaling up, with the metric of space itself stretching. This stretching of space is a subtle but profound concept. It means that the very ruler we use to measure distances is getting longer. If you had a cosmic tape measure stretching between two distant galaxies, and you could somehow keep it from being affected by local forces, you would find that the tape measure itself is stretching, increasing the distance between the galaxies. This is why galaxies aren't moving through space. The space between them is growing. This is a fundamental difference from objects moving through a static background, and it's what makes cosmological expansion so unique. The philosophical implications of this understanding are vast. It challenges our anthropocentric view of the cosmos, where we might instinctively place ourselves at the center of everything. The uniform expansion, with no discernible center or edge, suggests a universe that is fundamentally isotropic, looks the same in all directions, and homogeneous, looks the same from all locations on large scales. This is known as the cosmological principle, a foundational assumption in modern cosmology. It implies that the laws of physics are the same everywhere in the universe, and that our location is not special. This principle, while an assumption, is strongly supported by observations, particularly the remarkable uniformity of the cosmic microwave background. Furthermore, the idea that the universe is not expanding into anything external forces us to confront the limits of our own conceptual frameworks. We are accustomed to thinking in terms of containers and contents, boundaries and exteriors. But the universe, as the totality of existence, transcends these categories. It is a self-contained system, and its expansion is an inherent property of its own fabric. This can be a humbling realization, reminding us that the universe is far stranger and more magnificent than our everyday experiences might suggest. it pushes us to think beyond the familiar, to embrace the abstract, and to marvel at the sheer ingenuity of the cosmos itself. The universe is not just a collection of stars and galaxies. It is a dynamic, evolving entity whose very nature defies simple analogies and demands a deeper, more nuanced understanding. Let's further explore the implications of this stretching space on different scales. While the universe as a whole is expanding, this expansion is not uniform across all distances. On small, local scales, gravity dominates. Our solar system, for instance, is held together by the Sun's gravity, which is far stronger than the expansion of space over those relatively small distances. The Earth is not expanding away from the Sun, nor is the Moon expanding away from the Earth. Our bodies, our homes, and even the atoms that compose us are held together by fundamental forces that easily overcome the cosmological expansion. Similarly, galaxies are gravitationally bound systems. The stars within a galaxy are held together by their mutual gravitational attraction, and galaxies themselves are not expanding. In fact, galaxies can even collide and merge, like our Milky Way is destined to collide with the Andromeda Galaxy in a few billion years. These collisions are driven by gravity, which pulls the galaxies together, overriding the expansion of space between them. It's only on the largest scales, between gravitationally unbound structures like galaxy clusters, that the expansion of space becomes the dominant force, causing these clusters to recede from one another. This hierarchy of forces is crucial to understanding why we don't observe ourselves, our planet, or our galaxy expanding. The universe is a vast tapestry of structures, from the smallest subatomic particles to the largest superclusters of galaxies. On each scale, different forces dominate. On the quantum scale, the strong and weak nuclear forces and electromagnetism govern the interactions of particles and atoms. On the planetary and stellar scales, gravity holds systems together. And on the cosmic scale, the expansion of space driven by dark energy dictates the large-scale dynamics of the universe. This leads us to another fascinating, albeit speculative concept that often arises in discussions about the universe's boundaries: the multiverse. If our universe is expanding, and if it might be finite, could there be other universes? The idea of a multiverse suggests that our universe is just one of many, perhaps an infinite number, existing within a larger cosmic landscape. There are several theoretical frameworks that give rise to the multiverse concept. One popular idea comes from inflationary cosmology. The theory of cosmic inflation posits that in the very early moments after the Big Bang, the universe underwent an extremely rapid exponential expansion. This inflation smoothed out the universe, making it flat and homogeneous, and explaining the uniformity of the cosmic microwave background. However, some models of inflation, particularly chaotic inflation, suggest that inflation might not have ended everywhere simultaneously. Instead, it might continue indefinitely in some regions, while ending in others, giving rise to an infinite number of bubble universes, each with its own set of physical laws and constants. In this scenario, our universe would be just one bubble in a vast, ever-inflating ocean of space-time. Another concept is the many worlds interpretation of quantum mechanics. This interpretation suggests that every time a quantum measurement is made, the universe splits into multiple parallel universes, each representing a different possible outcome of the measurement. While this is a different kind of multiverse, it still implies an unimaginably vast number of coexisting realities. Then there's the idea of brain cosmology, which suggests that our universe is a three-dimensional brain, a membrane-like object, floating in a higher dimensional bulk space. Other brains, representing other universes, could also exist in this bulk, potentially interacting with our own. Collisions between brains, for instance, could be responsible for Big Bang-like events. While the multiverse remains a highly speculative concept, largely beyond our current observational capabilities, it offers a potential answer to some profound questions, such as why the fundamental constants of our universe seem so finely tuned for the existence of life. If there are countless universes, each with different physical laws, then it's not surprising that we find ourselves in one where life is possible. It's a bit like winning the cosmic lottery. If you buy enough tickets, eventually one will be a winner. However, it's crucial to remember that even within the context of a multiverse, the question of what those universes are expanding into still applies. If each universe is a self-contained entity, then its expansion would still be an intrinsic property of its own space-time, not a movement into an external void. The multiverse concept does not necessarily solve the fundamental paradox of expansion. It merely pushes the question to a larger scale. It suggests that the universe we inhabit is not alone, but it doesn't fundamentally alter the nature of expansion within each individual universe. It simply expands our cosmic perspective, hinting at a reality far grander and more complex than we can currently fathom. The search for evidence of a multiverse is an active area of theoretical physics, pushing the boundaries of our understanding of existence itself. The question of what the universe is expanding into, while scientifically resolved by understanding the expansion of space itself, continues to resonate with profound philosophical implications. It forces us to confront the limits of human intuition and the nature of reality itself. Our brains evolved to navigate a three-dimensional world governed by Newtonian physics, where objects move through a fixed external space. This ingrained perspective makes it incredibly challenging to intuitively grasp a universe where space itself is dynamic, where the container is part of the expanding content. One of the deepest philosophical questions tied to this is the concept of nothingness. If the universe is everything, and it's expanding, what was there before it? And what is outside of it, if anything? Modern cosmology suggests that before the Big Bang, there was no before in the temporal sense, and no outside in the spatial sense. Time and space themselves emerged with the Big Bang. This is a concept that challenges our linear understanding of time and our spatial reasoning. It implies that nothing in the cosmological context is not an empty void waiting to be filled, but rather the absence of space and time as we know them. This leads to discussions about the nature of existence. If the universe is a self-contained entity, expanding within its own fabric, then its existence is fundamentally different from objects existing within a larger framework. It is the ultimate container, the totality of all that is. This perspective can be both humbling and awe-inspiring. It suggests that our reality is far more intricate and self-referential than we might initially imagine. The universe is not a subset of something larger. It is the whole set. The philosophical implications also extend to our place within the cosmos. if there is no center to the universe, and every point is equally valid as an observational vantage point, it reinforces the Copernican principle that Earth and humanity do not occupy a privileged or central position in the universe. This idea, while initially unsettling to some, has been a cornerstone of scientific progress, pushing us to seek universal laws that apply everywhere, rather than anthropocentric explanations. Furthermore, the accelerating expansion and the potential for a big freeze or big rip raise existential questions about the long-term future of existence. If the universe is destined to become cold, dark, and empty, with all structures eventually dissolving, what does that mean for meaning and purpose? These are questions that science alone cannot answer, but cosmology provides the framework within which such profound inquiries can be posed. It forces us to consider the transient nature of even cosmic structures and the vast timescales over which the universe evolves. The ongoing quest to understand dark energy and the precise geometry of the universe is not just a scientific endeavor, it is a philosophical one. It's a search for the fundamental nature of reality, pushing the boundaries of what we can know and comprehend. The universe, in its elegant and counterintuitive expansion, continually challenges our assumptions and expands our intellectual horizons. It reminds us that the most profound truths often lie beyond the grasp of our immediate senses and require a willingness to embrace concepts that defy everyday experience. This journey into the nature of cosmic expansion is a testament to the power of human curiosity and the scientific method. From ancient philosophical musings to modern astronomical observations, our understanding of the universe has undergone a radical transformation. We have moved from a static, finite cosmos to a dynamic, expanding one, driven by mysterious forces and governed by laws that are both elegant and profoundly counterintuitive. The question, if nothing exists outside the universe, what is it expanding into, serves as a gateway to this deeper understanding, inviting us to shed our preconceptions and embrace the true, mind-bending reality of our cosmic home. Let's now consider some of the alternative cosmological models and ideas that have been proposed over time, and how they compare to the prevailing Big Bang model with its expanding space-time. While the Big Bang theory is overwhelmingly supported by observational evidence, scientific inquiry always involves exploring alternatives and refining our understanding. Before the Big Bang model gained widespread acceptance, one prominent alternative was the steady-state theory. Proposed in the late 1940s by Hermann Bondi, Thomas Gold, and Fred Hoyle, this theory suggested that the universe was eternal and unchanging on large scales, with no beginning and no end. To account for the observed expansion, Hubble's law, the steady-state theory posited that new matter was continuously being created throughout the universe, just enough to maintain a constant average density as space expanded. This continuous creation of matter was a radical idea, but it allowed the theory to explain the redshift of distant galaxies without invoking a Big Bang. However, the steady-state theory faced insurmountable challenges with the discovery of the cosmic microwave background, CMB, in 1964. The CMB, a direct prediction of the Big Bang, could not be explained by the steady-state model, which predicted a universe that would always look the same, without a relic radiation from a hot, dense past. the observed abundance of light elements also strongly favored the Big Bang. While historically significant, the steady-state theory has largely been abandoned in favor of the Big Bang model. Another class of models are those that propose a cyclic or oscillating universe. These models suggest that the universe undergoes an endless series of expansions and contractions, with each Big Bang being followed by a big crunch, which then bounces back into another Big Bang. This offers an appealing solution to the question of what came before the Big Bang, as it implies an eternal cycle. However, current observations of the accelerating expansion, driven by dark energy, pose a significant challenge to simple cyclic models. If dark energy continues to dominate, the universe will expand forever, preventing a big crunch. More complex cyclic models, sometimes involving extra dimensions or different forms of dark energy, have been proposed to overcome this, but they remain highly speculative and lack direct observational support. Then, there are theories that explore the nature of the Big Bang singularity itself. Some quantum gravity theories, such as loop quantum cosmology, attempt to resolve the singularity problem by suggesting that space and time are quantized at extremely small scales. In these models, the Big Bang might not have been a singularity, but rather a big bounce, where a previous contracting universe reached a minimum size and then rebounded into the expansion we observe today. This would mean our universe is part of a larger, potentially eternal, cycle of bounces, avoiding the need for a true beginning from nothing. These are highly theoretical frameworks, still under development, but they offer intriguing possibilities for understanding the very earliest moments of our cosmos. Finally, the concept of multiverse theories, as we touched upon, also offers an alternative perspective on our universe's place in a larger reality. While not directly challenging the expansion of our own universe, they suggest that our universe is not unique. Whether through eternal inflation, brain cosmology, or other mechanisms, the idea that our universe is just one bubble in a vast cosmic foam changes the context of its expansion. It implies that the question of what is outside the universe might be answered by other universes, each with its own expansion dynamics and physical laws. However, as noted, this doesn't negate the fact that each individual universe would still be expanding within its own self-contained space-time, not into an external void. In summary, while various alternative cosmological models have been proposed, the Big Bang model, with its inherent cosmic expansion and the recent discovery of accelerating expansion driven by dark energy, remains the most robust and observationally supported framework for understanding our universe. These alternatives, while fascinating, either lack sufficient evidence or face significant challenges from current data. The core idea that space itself is expanding and not into anything external remains central to our most accurate understanding of the cosmos. It is a testament to the scientific method that we continually test, refine, and sometimes overturn our most cherished ideas in the relentless pursuit of truth about the universe. The accelerating expansion of the universe, driven by dark energy, has profound implications not just for the ultimate fate of the cosmos, but also for the future of cosmology itself and humanity's place within it. As the universe continues to expand at an ever-increasing rate, the distances between gravitationally unbound galaxies will grow to truly astronomical proportions. This means that Over vast cosmic timescales, the universe will become an increasingly lonely place. Imagine a future billions of years from now. Galaxies that are currently visible to us, even with powerful telescopes, will recede beyond our cosmic horizon. The cosmic horizon is not a physical boundary, but rather a limit to what we can observe. It's the maximum distance from which light has had time to reach us since the Big Bang. As the universe expands, this horizon effectively shrinks for distant objects, meaning that light emitted from them will be stretched so much that it will never reach us, or will be stretched to such long wavelengths that it becomes undetectable. This is a consequence of the accelerating expansion. The space between us and distant galaxies is expanding faster than light can travel across it. This implies that future civilizations, billions of years from now, might look out into a night sky that is almost entirely empty. The vast tapestry of galaxies we observe today, each a universe of stars and wonders, will have receded beyond their observable universe. They would be left with only their own galaxy, and perhaps a few gravitationally bound neighbors, as the sole visible entities in the cosmos. This is a sobering thought, suggesting that our current era, where we can observe billions of galaxies, might be a uniquely privileged time in the history of the universe. The window to observe the grand cosmic structure is slowly but surely closing. This future isolation also has implications for our understanding of cosmology. If future astronomers can only observe their own galaxy, how will they deduce the Big Bang, the expansion of the universe, or the existence of dark energy? Their observations would be limited to a small, gravitationally bound island in an otherwise empty cosmos. This raises a fascinating philosophical question. Are we living in a special time, or is there a way for future civilizations to reconstruct the cosmic history we are currently unraveling? It underscores the importance of our current scientific endeavors as we are gathering data that might be forever lost to future inhabitants of the universe. Furthermore, the accelerating expansion challenges our ability to conduct certain types of astronomical research. For instance, studying the evolution of galaxies over cosmic time relies on observing galaxies at different distances, which correspond to different epochs in the universe's history. If distant galaxies recede beyond our observable horizon, our ability to study the early universe through direct observation will diminish. This emphasizes the urgency of current and future large-scale sky surveys and space telescopes, which are designed to capture as much information as possible from the distant cosmos before it becomes inaccessible. The concept of the cosmic horizon also highlights the inherent limitations of our observations. We can only ever see a finite portion of the universe, regardless of whether the entire universe is infinite or finite. This is not a limitation of our technology, but a fundamental consequence of the finite speed of light and the expanding nature of space-time. It means that there will always be parts of the universe that remain forever beyond our direct observational reach, forever shrouded in mystery. This is a humbling realization, reminding us that even with our most advanced instruments and theories, our understanding of the cosmos will always be incomplete. However, this doesn't mean the future of cosmology is bleak. Instead, it pushes us to develop new theoretical frameworks and observational techniques. Perhaps future technologies will allow us to probe the universe in ways we cannot yet imagine, using gravitational waves, neutrinos, or other exotic particles that are not affected by the expansion of space in the same way as light. The challenges posed by the accelerating expansion are also opportunities for innovation and deeper understanding. Moreover, the study of the universe's expansion continues to be a driving force for fundamental physics. Understanding dark energy, for instance, could lead to breakthroughs in our understanding of gravity, quantum mechanics, and the very nature of vacuum energy. It might even point towards new particles or forces that are currently unknown to us. The universe's expansion is not just a cosmological phenomenon, it is a laboratory for testing the most fundamental laws of nature. In essence, the accelerating expansion of the universe is a cosmic clock, ticking away, revealing and concealing parts of the cosmos over vast timescales. It shapes not only the physical reality of the universe, but also the very possibilities of scientific inquiry and the long-term prospects for intelligent life. It forces us to confront the transient nature of our cosmic view and to appreciate the unique opportunity we have in this moment to observe and understand the grand cosmic drama unfolding around us. To truly appreciate the revolutionary nature of the expanding universe concept, it's worth revisiting the intellectual landscape before Hubble's monumental discovery. For centuries, the prevailing view of the cosmos was rooted in a static, unchanging model. Isaac Newton's law of universal gravitation, while explaining the motion of planets within our solar system, presented a paradox when applied to an infinite universe. If the universe were infinite and filled uniformly with matter, then every star would be pulled equally in all directions, leading to a gravitational instability that should cause the universe to collapse in on itself. To avoid this, Newton himself suggested that the universe must be infinite and homogeneous, so that there was no central point for collapse. However, this still didn't fully resolve the issue of gravitational instability. Even Albert Einstein, whose general theory of relativity provided the mathematical framework for a dynamic universe, initially resisted the idea of expansion. When he formulated his field equations in 1915, they naturally predicted a dynamic universe, one that was either expanding or contracting. However, believing the universe to be static, Einstein introduced a term into his equations, the cosmological constant, specifically to counteract gravity and allow for a stable, unchanging universe. He later famously called this his biggest blunder after Hubble's discovery. The journey from a static to a dynamic universe was paved by several unsung heroes and theoretical insights. As mentioned, Vesto Slipher's meticulous spectroscopic observations of spiral nebulae in the 1910s provided the first hints of their recession. He measured the velocities of dozens of these objects, finding that most were moving away from Earth at speeds far greater than any stars within our own galaxy. While he didn't connect these redshifts to a general expansion of the universe, his data was crucial. Then came the theoretical breakthroughs. In 1922, Russian mathematician and meteorologist Alexander Friedmans, working independently, derived a set of solutions to Einstein's field equations that described an expanding universe. His models showed that a universe filled with matter could indeed be dynamic, either expanding or contracting, depending on its density. Friedman's work was largely overlooked by the scientific community at the time. partly due to the language barrier and partly because the static universe paradigm was so deeply entrenched. It was Georges Lemaitre, a Belgian Catholic priest and physicist, who truly put the pieces together. In 1927, 2 years before Hubble's publication, Lemaitre independently derived similar expanding universe solutions from general relativity. Crucially, he also combined these theoretical insights with the observational data available at the time, including Slipper's redshifts and early estimates of galactic distances. Lemaitre proposed that the observed recession of galaxies was a direct consequence of the expansion of space itself, and he even derived a linear relationship between velocity and distance, essentially Hubble's law before Hubble. He also put forward the revolutionary idea of a primeval atom, a highly condensed state from which the universe began, which is now recognized as the foundational concept of the Big Bang theory. Lemaitre's work, published in an obscure Belgian journal, also went largely unnoticed by the broader scientific community until it was brought to Einstein's attention. Einstein initially dismissed it, famously telling Lemaitre, "Your calculations are correct, but your physics is abominable." However, after Hubble's empirical confirmation, Einstein publicly acknowledged Lemaitre's foresight. This historical context highlights that the idea of an expanding universe was not a sudden revelation, but the culmination of decades of theoretical work and painstaking observation, with many brilliant minds contributing to its eventual acceptance. Hubble's 1929 paper, while not the first to propose expansion, provided the compelling observational evidence that could no longer be ignored. His meticulous measurements of galactic distances, using Cepheid variables as cosmic yardsticks, combined with the observed redshifts, presented an undeniable picture of a universe in motion. It was this empirical validation that truly shifted the scientific paradigm, leading to the widespread acceptance of the expanding universe and, subsequently, the Big Bang model. The universe was no longer a static backdrop. It was a living, breathing, evolving entity, and its expansion was the most fundamental aspect of its being. The expansion of the universe, while uniform on the larger scales, has played a crucial role in shaping the cosmic web, the intricate filamentary structure of galaxies and galaxy clusters that permeates the universe. This cosmic web is not a random distribution of matter. It's a vast interconnected network of galaxy clusters and superclusters, separated by enormous, relatively empty regions known as cosmic voids. Understanding how this structure formed and how expansion influences it is key to comprehending the universe's evolution. In the very early universe, immediately after the Big Bang, matter was distributed almost perfectly uniformly. However, the cosmic microwave background reveals tiny primordial fluctuations in density, regions that are ever so slightly denser or less dense than average. These minuscule variations, amplified by gravity over billions of years, were the seeds from which the cosmic web grew. In the denser regions, gravity began to pull more matter in, creating overdensities. In the less dense regions, matter was pulled away, leading to the formation of voids. As the universe expanded, these initial density fluctuations grew. Gravity worked to pull matter together, forming galaxies and galaxy clusters. However, the expansion of space simultaneously worked to pull these structures apart. It's a cosmic tug-of-war between gravity and expansion. On small scales, within galaxies and galaxy clusters, gravity wins, holding structures together. But on larger scales, the expansion of space dominates, causing galaxy clusters to recede from one another. The cosmic web, therefore, is a direct consequence of this interplay. Galaxies and galaxy clusters tend to form along the filaments of this web, where the density of matter is higher. These filaments are like cosmic highways channeling matter towards the densest knots, which are the massive galaxy clusters. The voids, on the other hand, are regions where matter has been pulled away, leaving vast stretches of relatively empty space. These voids are not truly empty. They contain some matter, but at a much lower density than the filaments and clusters. The expansion of the universe has been crucial in allowing this structure to develop. If the universe had expanded too quickly, gravity wouldn't have had enough time to pull matter together to form galaxies and stars. If it had expanded too slowly, the universe might have collapsed back in on itself before complex structures could form. The observed rate of expansion, finely tuned by the amount of dark matter and dark energy, has allowed for the formation of the rich and complex cosmic web we observe today. Furthermore, the cosmic web itself provides another powerful piece of evidence for the expansion of the universe. The distribution of galaxies on large scales, with its characteristic patterns and correlations, is precisely what is predicted by cosmological models that include an expanding universe originating from the Big Bang. By mapping the positions of millions of galaxies, astronomers can trace the evolution of this cosmic web over billions of years, providing a visual testament to the ongoing expansion and the growth of structure in the universe. The study of the cosmic web is an active area of research, with new telescopes and surveys constantly providing more detailed maps of the universe's large-scale structure. These observations help us to understand the roles of dark matter and dark energy in shaping the cosmos, and to test the predictions of our cosmological models. The cosmic web is not just a beautiful image of the universe, it's a dynamic, evolving structure that tells us a story of gravity, expansion, and the relentless march of cosmic time. The accelerating expansion of the universe paints a fascinating, if somewhat melancholic, picture for the very distant future of human civilization, or any intelligent civilization that might arise in our galaxy. As galaxies recede beyond our cosmic horizon, the universe will effectively become a vast, empty expanse, with only our own galaxy, the Milky Way, and its gravitationally bound neighbours, like the Andromeda galaxy, remaining visible. This era has been termed the Cosmic Dark Age. In this distant future, perhaps trillions of years from now, the night sky would be profoundly different. The familiar constellations would still be there, but the faint, diffuse glow of countless distant galaxies would be gone. Our galaxy would be an isolated island in a sea of ever-expanding nothingness. Any intelligent beings living in that era would have no observational evidence of other galaxies, no way to deduce the Big Bang or the vast cosmic history that led to their existence. Their observable universe would be limited to their own galaxy, and perhaps the remnants of the local group, the small cluster of galaxies that includes the Milky Way and Andromeda. This raises a profound question. If future civilizations are born into such a cosmic dark age, how will they ever discover the true nature of the universe? How will they know about the billions of galaxies that once filled the cosmos, or the accelerating expansion that drove them away. It suggests that our current epoch, where we can observe the cosmic web and the vast distribution of galaxies, is a uniquely privileged time. We are living in a moment when the universe is still transparent enough, and its expansion not so extreme, that we can piece together its grand narrative. This perspective underscores the immense value of our current scientific endeavors. Every observation we make, every piece of data we collect from distant galaxies is a precious record of a universe that is slowly but surely fading from view. It's a race against time, in a sense, to gather as much information as possible before the cosmic horizon shrinks further, taking with it the evidence of our universe's past. This is why projects like the James Webb Space Telescope, which can peer back to the earliest galaxies, and future observatories designed to map the large-scale structure of the universe, are so critical. They are our way of preserving the cosmic story for future generations, even if those generations can no longer observe it directly. Furthermore, the concept of the cosmic dark age highlights the potential for a fundamental limit to scientific knowledge. If the universe continues to accelerate its expansion, then eventually, even the light from the most distant parts of our own galaxy will be stretched beyond detection. Stars will burn out, black holes will evaporate, and the universe will approach a state of maximum entropy, a cold, dark, and empty void. This ultimate fate, the Big Freeze, suggests a universe where all physical processes eventually cease and all information becomes irretrievably lost. However, this bleak outlook is still billions, if not trillions, of years in the future. For now, we live in a vibrant, expanding universe, filled with wonders to discover. The accelerating expansion, while leading to a distant cosmic dark age, is also a testament to the dynamic and mysterious nature of reality. It forces us to confront the limits of our intuition and to embrace a universe that is far stranger and more awe-inspiring than we could ever imagine. The very fact that we can ask these questions and seek answers through scientific inquiry is a remarkable achievement, a testament to the power of the human mind to transcend its immediate surroundings and contemplate the grandest scales of existence. In conclusion, the question, if nothing exists outside the universe, what is it expanding into, is a profound one, but its answer lies not in searching for an external void, but in understanding the intrinsic nature of space itself. The universe is not expanding into anything. Rather, space itself is stretching, carrying galaxies along with it. Much like raisins in a rising loaf of bread, this expansion is happening everywhere, uniformly on large scales, meaning there is no center and no edge to the universe in the traditional sense. Our understanding of this cosmic phenomenon is built upon decades of meticulous observation and groundbreaking theoretical work. From Edwin Hubble's discovery of the expanding universe to the detection of the cosmic microwave background, and most recently, the astonishing revelation of accelerating expansion driven by dark energy. Each piece of evidence has refined our picture of the cosmos. We've learned that cosmological redshift is not just galaxies moving away, but light waves stretching as space expands. We've discovered that the universe began from an incredibly hot, dense state and has been evolving ever since, with its ultimate fate tied to the mysterious properties of dark energy. The implications of this understanding are vast, touching upon the very nature of reality, the limits of our intuition, and our place in the grand cosmic scheme. It challenges us to think beyond our everyday experiences and embrace a universe that is far more dynamic, complex, and awe-inspiring than we could ever imagine. Whether the universe is infinite or finite but unbounded, its expansion is an inherent property, a continuous creation of more space from within its own fabric. This journey into the heart of cosmic expansion is a testament to the relentless human quest for knowledge. It reminds us that the universe is not a static backdrop, but a living, breathing entity, constantly evolving and revealing new layers of mystery. As we continue to explore the cosmos with ever more powerful telescopes and sophisticated theories, we are not just observing distant stars and galaxies. We are unraveling the fundamental laws that govern existence itself. The universe is a boundless source of wonder, and its expansion is a continuous reminder of its infinite capacity for surprise. Join us as we continue to delve into the depths of the cosmos, unraveling its mysteries, one mind-bending concept at a time. The universe is calling, and its stories are just beginning to unfold. Be part of the journey, subscribe to CosmoDepth, and together, let's explore the wonders that lie beyond. The cosmos awaits, and its secrets are slowly but surely revealing themselves to those who dare to look. So, what have we learned from this journey into the expanding cosmos? We've come to understand that the universe is not a static entity, but a dynamic, evolving one, constantly stretching its own fabric. This expansion is not into some pre-existing void, but an intrinsic property of space-time itself. It's a concept that challenges our everyday intuition, but one that is firmly supported by a wealth of observational evidence, from the redshift of distant galaxies to the faint afterglow of the Big Bang, the cosmic microwave background. We've explored the mysterious force of dark energy, the enigmatic driver behind the universe's accelerating expansion, a force that dominates the cosmic landscape and dictates its ultimate fate. We've grappled with the idea of a universe that may be infinite or finite, but unbounded. A universe with no center and no edge, where every point is equally valid as an observational vantage point. And we've touched upon the profound philosophical implications of this understanding, forcing us to reconsider our place in the cosmos and the very nature of reality. The universe, in its elegant and counterintuitive expansion, continually challenges our assumptions and expands our intellectual horizons. It reminds us that the most profound truths often lie beyond the grasp of our immediate senses and require a willingness to embrace concepts that defy everyday experience. The question, if nothing exists outside the universe, what is it expanding into, serves as a gateway to this deeper understanding, inviting us to shed our preconceptions and embrace the true, mind-bending reality of our cosmic home. This journey into the heart of cosmic expansion is a testament to the power of human curiosity and the scientific method. From ancient philosophical musings to modern astronomical observations, our understanding of the universe has undergone a radical transformation. We have moved from a static, finite cosmos to a dynamic, expanding one, driven by mysterious forces and governed by laws that are both elegant and profoundly counterintuitive. The universe is not just a collection of stars and galaxies, it is a dynamic, evolving entity whose very nature defies simple analogies and demands a deeper, more nuanced understanding. The cosmos is a boundless source of wonder, and its expansion is a continuous reminder of its infinite capacity for surprise. Join us as we continue to delve into the depths of the cosmos, unraveling its mysteries, one mind-bending concept at a time. The universe is calling, and its stories are just beginning to unfold. Be part of the journey, subscribe to CosmoDepth, and together, let's explore the wonders that lie beyond. The cosmos awaits, and its secrets are slowly but surely revealing themselves to those who dare to look.